Yeah, so we are now going to the second discussion session of the day, which is going to be on IC engine sprays. Before we begin, I would like to thank the organizers for inviting us and for giving us this opportunity. Myself and Professor Jeff Neighbor will be chairing this session, and we have decided to do something a little different in this session. We are going to actually have a panel discussion, so which means that after I give a few introductory remarks, we will have about 4 panelists. We'll request each one of them to come and share their views on what are the challenges that we face in dealing with engine sprays. And then we will have some discussion, and then at the end, my co-chair, Professor Jeff Neighbor, would summarize and probably provide some directions for future work and opportunities for collaboration. So here are the panelists who will follow me. Professor John Abraham from Purdue, Professor Marcus Herman from Arizona State University, Dr. Sibendu Som from Argonne National Lab, and Dr. Shamit Bakshi from IIT Madras. Actually, before I really get into listing out the points for discussion, I would like to emphasize one issue. Now, when we talk about IC engines, it is not only about transportation. There is also stationary power generation, which is an important application. Now, when we talk about automotive applications, we all know there are extremely stringent emission norms. The requirements are very different. Whereas for stationary power generation applications, well, there are also emission norms, but there is a wider adaptability of various fuels, including biofuels. The issues are somewhat different, maybe not as challenging as in automotive applications, but a different set of challenges. So what I'm going to do in the next few minutes is show some of the work that we have been doing with respect to using plant oil biofuels as engine substitutes. Now, when I say plant oil biofuels, I'm referring to non-edible plant oils such as Jatropha, Pongamia, which I'm sure many of you are familiar with. And I'll just briefly show you some work that we have done to just kind of highlight the challenges that we face when we deal with very new biofuels because of their very different properties and so on. So I'll just spend about 5 minutes just to give a flavor of some of the things, and then I'll come back to the points of discussion. This is a high pressure chamber that we have in our laboratory, and we have done some controlled experiments in a quiescent environment, of course, and at high pressure and high injection pressure and gas pressure. And we have used the PDI technique. Now, I'm talking about this technique because I'm going to show you some near nozzle images which are of interest, I think, to our community in general, particularly to the community that deals with primary atomization. Because I'll show you a couple of images that we have recently obtained, which I hope will probably give us some food for thought. So Dr. Som earlier talked about the Argonne National X-ray facility, which gives you a very detailed information. I'm going to show you something that we were able to achieve with a somewhat simpler technique, definitely far simpler than the X-ray technique. This is your standard shadowgraphy, but of course this technique has been improved over the last several years, primarily with respect to use of high-powered lasers and also long-distance microscope with fairly high resolution cameras. This combination of these two has really helped us to probe into the near nozzle structure, and I'm going to show you some images later on. Of course, this is just a picture of that. Now, in fact, when we actually started looking at these oils, we found something extremely interesting. We did find that this is just a conventional diesel injection image, and when we looked at Jatropha and Pongamia oils, these are, by the way, these are the plant oils which have not been esterified, so they are not biodiesel, they are the actual original plant oils. And we found something extremely strange. Now, these are injections over 1000 bar pressure, and we were really shocked to see almost an intact liquid core when you inject at pressure. Close-up images, as you can see, if you increase the injection pressure to something like 1600 bar, you still actually get an intact liquid core, which is really, I was really shocked when I saw that. And you just see that the effect of the injection pressure is just to increase the actual diameter of this core, and that just reflects in the higher mass flow. Now, just to give you a quick idea about the importance of research in biofuels, if you look at the properties, The viscosities are of course pretty high compared to that of diesel. Okay, they're roughly about 7 to 8 times higher than diesel. But more importantly, I want to show you this diagram. Now, this is a famous diagram where you have Onsorg and the Reynolds number, and diesel of course somewhere lies here, as we all know, in the atomization regime. Now, if you were to calculate the properties of these oils, you would expect them to lie here in the second wind-induced regime. However, what you see experimentally is very different. You know, they don't look as if they lie here. So that's what made us suspect that there must be some non-Newtonian behavior. And this was indeed confirmed. Of course, this is from the literature. This is from a paper back in 2006 where there was some work on olive oil was done. By the way, these oils are all fairly similar in behavior. Of course, the fatty acid compositions are somewhat different, but they tend to behave in a similar direction, I mean in a similar way. And you see that there is a 6-fold increase in viscosity over typical diesel injection pressure. So you go from 0 to about 1400 bar, there's a 6-fold increase in viscosity of oil. And when we did a simple experiment with Pongamia oil, and this, it's very similar to Jatropha also, sorry, we did notice some evidence of non-Newtonian behavior. If you look at the dynamic viscosity shear rate, there is a nonlinear variation which tells us that there is non-Newtonian behavior of these oils. And it's interesting that when you look at blends, now blends is something which is also going to be of very interest to us, whether it's gasoline or maybe even diesel, and the spray is significantly affected by the presence of the blends. So if you have a 50% blend of this oil, of this non-Newtonian highly viscous oil with diesel, you will see how the core has changed, and of course it changes drastically as you reduce the amount of oil. So these are just pictures for you to keep in mind. The other important point is what was I think raised in the previous session about how to quantify or how to detect the presence of ligaments. How do you know that there are ligaments, or how do you know that there are not spherically or spherical droplets? So in fact, even in diesel, when we looked at injection pressures into being injected into ambient environment, we do notice that there is a presence of ligaments. Of course, this is a little bit later because early on in the spray it is so dense that it's impossible to visualize anything. But of course, this is at ambient pressure, but if you increase the gas pressure, things do change. I'm just showing you some of these just to give you a flavor of some of the issues involved. Now, this is the kind of near nozzle structure I was talking about, and possibly a technique like this could, along with the X-ray data from argon, could probably help the community in trying to understand or assess primary atomization, and the modeling efforts could probably combine with experimental efforts. Now you see that this is just about 1 millimeter from the nozzle, and again you see that the effect of the gas pressure, as we all know, does play an important role. Of course, the injection pressure is of the order of 1000 bar, and this is just the gas or the environment pressure. You do see that there is a drastic change in the primary atomization. Of course, this is of course towards the end of injection, so I'm not shown any images. But what is more interesting is, of course, if you compare the so-called Pongamia, of course, the diesel should be here, it's just got shifted. So this is Pongamia, this is a 50% blend, 20% blend, and this is diesel. You can see that the effect of the oil has a drastic impact on the atomization structure. You can see that there's just intact core at very high injection pressures. So I think there is scope for more simpler techniques like this, maybe combined with the X-ray technique, to give us a better understanding. And I'm sure data such as this would probably in some sense or in some way help the primary atomization modeling community also. And of course, the tip penetration schemes are very different, and I'll just skip some of these just to show that there is a need for spray tip correlations also. And this is of course some Sauter mean diameter distribution from the LSD technique, which I think many of you are familiar with. Yeah, this is one thing that I want to just present before I go to discuss the points to be raised. Now, you look at diesel and Pongamia, of course Karanja is the local name for Pongamia. The liquid fraction distribution is very different. Now, this again in some sense may have an effect on the entrainment, and this may lead to some very interesting conclusions about what Professor Abraham was talking to us yesterday about the behavior of a gas jet being similar to that of a liquid jet. So if there are fuels with very different properties, then some of these issues could also come up. We don't know. I mean, these are open issues. So I'm going to come now to the points of discussion. Of course, primary atomization, what is the effect and how sensitive are the details to the overall spray structure? So the question is the current state of the art good enough to help us understand what happens to the resulting spray structure? And of course, of more interest to the community, the industrial community, what kind of hybrid modeling approaches are available? And is there a good approach which takes the data from primary atomization modeling and through either LES or other approaches and feedback to the standard arbitrary Lagrange and Eulerian kind of simulations? And of course, what is the impact of nozzle internal geometry? We had a very interesting talk by Professor Steve Collicott from Purdue yesterday, and sort of gave us a lot of idea about the effect of cavitation. So this is again very important, the cavitation and its effect on spray structure. And Professor Jeff Neighbor mentioned yesterday about the challenge of transient events. When you have multiple injections, how does the spray structure behave? How do the droplet sizes, what are the droplet sizes, and so on. Of course, finally, the effect of fuel properties, about which I've already given you a little bit of a flavor earlier. What role does it have on spray structure? Of course, I took a very extreme example of a highly viscous non-Newtonian oil, but I'm sure that these issues are going to be relevant for us when we look at any biofuel. And some of the issues with biofuels, in my opinion, and of course we could have a lot of discussion on this. Of course, some of it is from the literature, that nozzle cavitation, maybe, I'm not sure whether it will work for biodiesels. Of course, the penetration is higher and flow rates are lower for some of these biodiesels. Again, the liquid length, lift-off length have been reported to be different for combusting sprays. Biodiesel is found to show slower breakup, and there are larger droplet sizes reported for biodiesels. And of course, evaporation rates are different. But then there are again other issues with biofuels. Again, with respect to the nozzle geometry. Now, it's probably desirable to have cavitating flow, but is it possible to control cavitation? Is it possible to obtain a very repeatable spray? And this again is very interesting in the context of biofuels. And could it be just be geometry, or could there be some flow control strategies like Professor Stephen Collicott was telling us yesterday? So these are some open questions. And of course, finally, with biofuels, you may have to deal with non-Newtonian behavior. Now, what effect is it going to have on spray structure and secondary breakup? I know Professor Paul Soika has been working in this area very actively, and it would have been nice to have him here to shed some light on this.
Let me just say one thing. We are going to the site talk at 4 o'clock this afternoon.
Great, that's good. Finally, I'll come to the last slide. Now, the points for discussion on gasoline sprays. Now, again, Professor Neighbor showed us yesterday about the challenges with dealing with GDIs, the dynamic spray structure, and of course, the effect of nozzle geometry, then fuel blends. You have ethanol and other fuels being blended with gasoline. And finally, on gasoline sprays, we have to look for some synergy between modeling and experimentation. Now, I think there are several people here in this room who are involved with the ECN. I know Professor Abraham, Dr. Som are all involved. Maybe they can throw some light on what are the efforts of the ECN network and how maybe our community can, in our own way, contribute to these efforts. So with that, I'll stop here, and I would request Professor John Abraham to maybe comment on these issues or educate us on some of the...
Okay, thanks, Ravi, for those pictures are just amazing and very interesting. Very informative as well, so I'm impressed. So I want to continue the discussion by talking a bit about my, again, this is now become really opinions. My opinions about spray research in the IC engines area that can have an impact on engine development. And I keep coming back to this because I worked in industry for some time before going to academia. And I know, I think I know how the industrial, the person in the industry is thinking. And as part of my research in academia, I interact very closely with several engine companies. And so you always have this challenge of trying to convince them that what you're doing is actually beneficial and useful. But so as a background, research is carried out in a time of increasingly constrained funding resources in the US. Listening to what Mahesh was saying about the funds being available in India, that doesn't seem to be the case. But at least in the United States, it's in increasingly constrained funding resources. So we are forced to address broader impact and impact questions and impact on the US economy. So anything we do has to be justified. And to some extent, that is reasonable, right? I mean, if we think about it, that is reasonable. There are many interesting questions which are fundamental and worth doing, worth answering, and science is worth just pursuing for its beauty and its truth, and that's just great. But ultimately, we have to be able to explain to people why this research that we are doing would have an impact on their lives. So when we talk about engines, we always have to think about one, how does what I do improve the efficiency? And improving the efficiency indirectly in internal combustion engines means that, of course, you're saving fuel, but also you're cutting down on carbon dioxide emissions, right? And then how do you reduce emissions of toxic pollutants? How does any change or whatever I do to the spray in the engine have an impact on toxic pollutant emissions, particulate matter, carbon monoxide, nitric oxide, and so on. And of course, the customer always wants to have good performance and high reliability for the product that is being used. So yesterday in my talk, I pointed out that there are two areas where I do believe that research in sprays can have a significant impact. And both of these I would classify as advanced combustion engines as distinct from, say, the port fuel injection or multi-point injection engines that are commonly available today, where the advances are likely to be small and incremental at best. Okay? But these two concepts that I'm going to talk about are concepts where if we can improve our understanding of sprays and the modeling of those sprays, it can have a significant impact. The first is direct injection spark ignition. Also, this has been referred to as gasoline direct injection this morning by Ravi and also by Jeff yesterday, engines. And these are different from the port fuel injection engines that we use in our cars, in the sense that the fuel is injected directly into the cylinder, as I explained yesterday. But when you're injecting directly into the cylinder, you're typically injecting at lower injection pressures than when you directly inject the fuel in a diesel engine. And not only that, the timing of injection can vary significantly depending upon the load that you require. At high loads, you inject it very early, so you get sufficient time for the fuel and air to mix. At light loads, you inject it late, so the fuel and air do not mix very well. The challenge with the engines is that emissions tend to be high. So that is the focus. So if industry can find a way, or if we can provide an answer to industry which says that doing this will cut down emissions, and the emissions of interest are unburned hydrocarbons, carbon monoxide, particulate matter, nitric oxide. If my spray research can make an impact on cutting down the emissions of these species, it will make a difference to the manufacturer and to the economy. Injection pressures vary from 10 to 200 bar in these injectors, and the injection momentum is at lower pressures can be sufficiently low that the ambient flow field can influence the spray development, and it is also possible that the ambient flow field can possibly affect secondary atomization. Okay, so there is not only the primary atomization, which would be interesting to understand, but it is possible that if you have a very highly swirling flow field, or if you are injecting during the intake stroke when you have this very high velocities coming in through the intake valves, then that can induce secondary atomization. And so understanding those mechanisms are very important, and it can have an impact on engine development. In these engines, the spray, the liquid, when I say the spray, it's not so much the gas phase of it, but the liquid phase of the jet of the spray will interact with the walls. I mean, there's no question about that, because it doesn't vaporize as rapidly as it does in a diesel engine. So understanding interactions of the liquid phase with walls, if you inject at a certain pressure, at a certain crank angle, if you can tell the engine manufacturer so much of that spray is going to impact on the wall, and of the spray that impinges on the wall, 10% is going to remain as a liquid. The thickness of the film is this much. If you do that, that is a significant input to the engine manufacturer. Okay, and it can have a significant impact. So interactions of the liquid phase with the walls is very important to understand. And this is just an additional point to keep in mind, that these engines operate in homogeneous and stratified charge combustion. So both of those are important depending upon the load that you run the engine at. So this is an advanced combustion engine. And I mentioned yesterday that there are different ways in which the fuel injection is achieved. Fuel injection can be achieved, and the spray development can be achieved through interactions with the wall directly, or through interactions with the flow field, or you can have multiple sprays that interact with the spark plug. Okay. Now, the second advanced engine concept is low temperature combustion engines. And I want to make this clear that these are non-EGR engines, because you can have a conventional diesel engine running as a low temperature combustion engine if you use excess of exhaust gas and recirculate it, right? So that becomes an excess inert environment where the temperatures can be kept low. But I'm not referring to that specifically. But that has its own challenges, but not necessarily so much related to sprays. But the low temperature combustion engines, these low temperature combustion engines are very similar in some sense to the DISI, GDI engines that I talked about on the previous slide. The challenges with this, once again, emissions, carbon monoxide and unburned hydrocarbons, especially at light load, and control of combustion rates at higher load. Okay, those are two significant challenges. Okay, so obviously anything that we do, we have to direct it to address these challenges that the industry faces. Injection pressures, as in the previous case, can vary from 10 to 200 bar, depending upon when you decide to inject. Now, if you want to run a low temperature combustion engine as a homogeneous charge compression ignition engine, so it is more like our port fuel injected engines, okay, then of course injection has to be very early in the cycle during the intake. And then just as in the direct injection engines, the fuel and air mix and become homogeneous, in these engines they become homogeneous too, in which case you will use fairly lower pressures. These are just representative numbers I put. But if you do that, then the ambient flow field influences the spray development, and just as in the DIS engines, possibly secondary atomization. And again, as in the DISI engines, interactions of the liquid phase with the walls become very important. In these engines, the spray impinges on the wall. There's no question. It is known. So this is something that needs to be addressed, and the same kind of questions I raised just a couple of minutes ago come up in these engines. And DISI engines, homogeneous and stratified charge combustion are important. Stratified charge is essentially how you try to regulate your emissions and try to regulate your load. So this is almost a mirror of the GDI engines, except that here you achieve combustion through compression ignition. In the other case, you achieve it through spark ignition. Again, these are the kinds of concepts. You can have a injector located, and you can have a hollow cone spray, or you can have full cone multi-hole sprays. In fact, this particular experiment, I referred to this yesterday, was done at Sandia, and they just took a standard GDI injector and put it into a diesel engine, into a compression ignition engine to run it. So that's because they operate very similarly, except for how combustion occurs. And of course, once you get this stratified charge, you can have stratified charges in the chamber, and this picture I showed yesterday as well. Now, the assumption we make when we pursue these research topics is that these advanced technologies will continue to be of interest to industry. But I think that's a two-way coupling problem, right? Because if as academic researchers we can address the issues that industry faces fast enough, if we can address the issues that they're not going to wait around for 15, 20 years for research to be accomplished, right? But if we can address it fast enough, then maybe they will continue to have interest and develop it. So it's a two-way coupling problem that needs to be kept in mind. So obviously, in all these sprays, GDI sprays, LTC sprays, drop size distribution as input for models in low to mid pressure injection, full cone and hollow cone sprays are important to know. Interactions of liquid phase with walls, and the impact of this interaction is important to understand. Secondary atomization, not just the secondary breakup that takes place in sprays, but secondary atomization as a result of interaction with the flow field, and possibly with the walls too, right? It's important to understand. And after listening to my colleague, Steve Collicott, influence of internal design of nozzles probably is important to understand, and Jeff too, he brought it up too. And of course, alternative fuels, what is the impact of using alternative fuels on these parameters of interest? But numerical accuracy is just as important. I see a lot of results where you get spray penetration agreeing within 10%, flame liftoff agreeing within 10%, and Sibendu, maybe you're going to show this. So, so this is not a reference to what you're going to show, but but I do see it. And I'm not so sure that you can get the right answer with the wrong numerical parameters. And so, I mean, this is and when you talk to people in industry, this is one of the biggest problems they face, because we overpromise things to them by showing them pretty pictures and results, and then when they get it and try to use it, they find that they can't. So there, they get terribly disappointed. This happens, okay? So numerical accuracy is extremely important to keep in mind, and do not believe everything you see with models. Computational speed is, of course, important. I mean, industry would like to get something which is they can do overnight on a computer, right? But I think the more important thing is accuracy. If we promise if you tell them the truth and show them things the way they work, they're wrong, then tell them they're wrong. I think that we will gain more credibility, and credibility is often lost. Models in conjunction with experiments are powerful tools. That's true, whether we use it as a research tool or not. But I do not believe they are predictive over certainly a wide range of operating conditions in engines. They are not.
Okay, thanks. I was a bit of a last-minute addition to this panel, so I'm just going to have 2 slides, and then I'm just going to talk about some of the issues I think that we still face with simulations. And I'm going to go down into the trenches a little bit and just focus on primary atomization. And the question is really, do we have a truly predictive model for primary atomization? And I would venture out to say, no, we don't. Because we have models that we typically have to tune. So we need experimental data. We tune our models to that experimental data. And then we can do predictions in between experimental measurement points. So we can interpolate with some confidence, if I'm so bold to say that, between experimental data that we have. Plus, we have certain models, and we put them in simulation tools that are prone to numerical accuracy issues, as just mentioned. So we're not only tuning our models to the physics, but we're also tuning it to our bad numerical accuracy that we have. So there's an overlap between the two. So that being said, and having dissed all primary atomization models maybe, the question is, can we do something more? Can we try to predict atomization from a little bit from first principle? And that's where detailed simulations come into play. Now that's at the complete opposite spectrum of computational cost than what industry is looking for in overnight simulations. So you have to think about these more as a numerical experiment and think about experimental time frames of setting up an experiment, running the experiment, repeating the experiment. So we're not talking overnight, we're talking weeks or months in the end. So the question is, can we study primary atomization, understand the physics of primary atomization, doing detailed simulations, and the benefit being that we don't have any limitations of probing the data otherwise, which you might have with experimental data. You don't typically have the full four-dimensional data set available with all quantities you're interested in. A simulation would give you that, but then you run into the problem, of course, with the simulation, can I believe those issues? And I'm going to talk about that later in one of the other discussion sessions. So here I'm going to just show you 2-3 examples of people that have done primary atomization simulations. And I say it's IC engine, it's diesel type injections. So you inject a turbulent liquid into compressed air. And there's no other geometric complexity involved. It's basically into an open box, and you might or might not have the turbulent pipe of the injector upstream of it taken into account in the simulations. And here are 2 snapshots. One is from Olivier Desjardins. The other is from Bellamont's group, MENA, from 2008 and 2007. And there are other examples, Shinji Omamura and Bo from Glim's group, and probably many others. And we've done some work in this as well. So let me just show you this one movie of a turbulent liquid jet into compressed air. The Reynolds number here is 5,000. The Weber number is 17,000. And the grid resolution here is 128 points for the interface across the injector diameter, which is 100 micron. And you see this atomization happening. And the individual spray drops that are generated are color-coded in yellow here because the description of it changes. So we can try to do these simulations and try to look at the impact of certain properties of Reynolds number, of Weber number, of turbulence, of liquid turbulence on the actual atomization process. Now, with those things having been shown, and I would say, yes, that might be true in the mean, and there was some convincing evidence that it behaves like that in the mean, but what about the fluctuations? What about the variance? What's the impact of fluctuation variance on pollutant production? Is pollutant production dominated by the mean behavior, or is some of the soot formation processes maybe dominated by the fluctuation parts? And how well do I capture these fluctuation parts if I do a pure gas jet approximation? Maybe something to be looked at. So I wouldn't completely discount these primary atomization, these liquid type models. Then the other thing is, when we do these type of simulations, for the primary atomization part, we're just looking at the very, very near injector part. But the simulation I showed you was 25D diameters in the near injector part. So with a 100 micron nozzle, that's 2.5 millimeters. That's a tiny, tiny fraction of the entire engine, of course. So we can do these near nozzle flows, and then we have to transition to some Lagrangian description, as we do. And then secondary atomization could kick in, presumably. The question is, how much secondary atomization is actually happening still if you actually do a detailed simulation of the primary atomization? Now, traditionally, if we try to model these things, we're basing our models to a large extent upon secondary atomization ideas and the experiments that were done for single drop atomization. Right? We know how these break up, and we try to push this in some of these very simple models. We try to push these ideas to the very near injector region. And then look at, yes, those larger drops will break up to form as our final drop size distribution. But in the absence of auxiliary flows, like described, where we introduce additional shear to it, how much secondary atomization is actually happening after we've broken up this primary jet in the near injector region? And we tried to look at that, and we activated stochastic secondary atomization models, and we find not very much secondary atomization is still happening. It all depends, of course, on what do I define as primary atomization. I might have big blobs breaking up at the leading tip. Do I call this the end of primary atomization? Then these big blobs will, of course, continue to break up in a secondary atomization model. Or do I continue the breakup? Oh, I'm good. Do I continue to call this big blob and follow it and call primary atomization the fate of this big blob that has broken up into smaller? So it's a little bit of a definition issue in some extent. Then the other thing I wanted to touch upon, because the experiment's just shown, biofuels. There was this strikingly different behavior in the biofuel jet compared to the diesel jet. From a modeling perspective, and this was attributed to non-Newtonian behavior, right? But if I look at this from a modeling perspective, what goes into these type of simulations are characteristic numbers. It's the Reynolds number, it's the Weber number, and yes, the Ohnesorg number and any derived quantities from that. If I look at those characteristic numbers, the Reynolds number was strikingly different. And we see in our simulations that turbulence might not cause the actual breakup, but surely initiates the instability modes that will then finally cause breakup. So first question is for these biofuel things, if the Reynolds number is so different, do we actually have a turbulent inflow? Or is it a laminar inflow? Because there have been simulations by Jinyu and Umemura where I do a laminar jet instead of a turbulent jet that show very, very long, unperturbed interfaces, basically, very similar to these experiments. Whereas if we put in turbulence, we see a very quick breakup. And it also depends on what turbulence we put in. Do we put in turbulence from a, let me say, real turbulence from a turbulent pipe flow simulations that we do auxiliary and use real-world turbulence, as far real-world turbulence with a simulation goes, use that as an input condition, we see streak structures imprinted on the jet. We see that in our simulations, Olivier simulations as well. But if we use artificially generated turbulence by a procedure by Klein, where we just do a statistic type of reproduction or regeneration of turbulence without the actual pipe flow, we see a somewhat different behavior. It seems to be an impact of turbulence, which could relate to these biofuel applications because the Reynolds number is so different. Which brings me back to that point is, are all liquids that we inject characterized by the typical characteristic numbers we have in their entirety? Is it Reynolds number, Weber number, and Ohnesorg number only? Or is it some additional physics like non-Newtonian behavior that's important? It's maybe something to look at. Then in terms of challenges, what are the open questions? Many simulations that are done for these type of injection behaviors in stagnant compressed air are done at parameter regimes that are maybe no more fully relevant to the IC engine manufacturers. They're maybe 10, 15 years behind the curve in terms of injection pressures and properties. And that relates to the question of, are we supercritical, subcritical, or transcritical? Many of the formulations we use today are in the low Mach number incompressible regime. So we don't really take equations of state fully into account. We treat them as constant density approximations in each phase. How much does that impact? Then the question is, if we do these low Mach number approximations and the injection velocities spike, go up. I mean, the example I showed you was 100 meters per second injection velocity. So the Mach number was relatively low. So if you go to higher injection pressures, the velocity spike, we probably can't get away with low Mach number formulations anymore, which directly relates to the transcritical, supercritical behavior where we have to go fully compressible with equations of state anyway. Then the question of the internal flow that comes into play. We've seen some indications that internal flow is important, as I just talked about what turbulence or if turbulence and what quality of turbulence we input into these simulations. And it's very much conceivable that the internal geometry, of course, plays an important role if there is cavitation. especially if there's cavitation in there. Even if there isn't cavitation, it might make a difference in the needle movement. If you have the needle moving back, and there have been some very interesting studies at argon that look at the needle movement. The needle pulls back and then it jiggles around. What's the impact on that on the injection velocity, right? It will impact something. Does that impact my primary atomization characteristics? Very likely. So those things can be looked at, and you have to develop these type of methods that exist, or model numerical techniques that exist in other areas, and bring them to these type of simulations as well. And then finally, the multi-component nature of the fuel. And that's where I really get scared, because if I do evaporation, or if I do injection in hot environments, I evaporate, but I don't evaporate the species at the same time. So I can, of course, dynamically change my material properties in terms of viscosity, surface tension behavior. Leaving aside for a second that my temperature variations, of course, will impact my local surface tension coefficients, thereby changing my local Weber numbers drastically, and thereby changing my atomization characteristics, which is all not taken into account in these type of initial simulations where we assume constant temperature, constant surface tension coefficients. But if we talk about multi-component evaporation and multi-component fuels, that all comes into play. So in terms of a reference fuel, I'm just purely happy with the single component fuel, just to look and study primary atomization, realizing that that is a significant simplification, unusable for the combustion part at the end of it, but I'm simplifying a lot probably the primary atomization characteristic, very definitely what happens later on in terms of the dynamics of the spray itself. So that's what I had basically in terms of detailed simulations, and trying to find a way of improving the models that we use or the models that we might be able to use in industrial setting down the road, using detailed simulations to study that and improve the knowledge that we have in those type of models.